What if a whisper from a galaxy 2.5 million light-years away could shake the invisible shield protecting our planet? On October 1st, 2025, something rattled Earth's Van Allen radiation belts, and the source wasn't our sun. It was a faint 8-second signal from the direction of Andromeda. NASA is scrambling, and the data points to a connection we never thought possible. This isn't science fiction, it's a developing mystery with profound implications. Let's explore this together.
The October 1st discovery.
It all started with a routine alert that was anything but. High above our heads, a vast field of radiation called the Van Allen belts protects us. On October 1st, 2025, NOAA's Space Weather Prediction Center issued a G2 geomagnetic storm watch, a moderate alert corresponding to a KP index of 6. Nothing unusual. But then, Mission Control at Goddard Space Flight Center noticed strange chatter. Automated queries to the legacy data from the Van Allen probes mission, which orbited up to 30,000 kilometers high, began spiking. The mission, operated by the Johns Hopkins Applied Physics Laboratory from 2012 to 2019, had its archives pinged hundreds of times in an hour, a clear emergency pattern. As noted by experts like Dr. Daniel Baker, a leading figure in radiation belt physics, this wasn't routine analysis. The automated pull focused on data from the Relativistic Electron-Proton Telescope, or REPTT, suggesting a specific and urgent concern about high-energy particles. These algorithms were specifically looking for anomalous acceleration gradients that didn't fit known solar wind coupling models. This high-level digital scramble indicated that the system had flagged a change in the belts that was not only significant but also fundamentally strange in its origin.
The anomalous signal.
So, what exactly did we hear? The first clue didn't come from a weather satellite, but from the Deep Space Network's 70-meter dish in Goldstone. At precisely 3:47 UTC, radio telescopes logged a strange transient lasting only 8 seconds from the Andromeda sector. The problem? Its signature matched nothing in the catalogs. The burst peaked at 408 MHz, a frequency once used for old UHF television channels, and far softer than most fast radio bursts, which typically range from 400 MHz to 8 GHz. Its flux density was incredibly faint, estimated at less than 0.5 Janskis. To put that in perspective, the famous radio source Cygnus A is over 7,000 Janskis at the same frequency. This signal was a true needle in a haystack. Radio astronomers were baffled by its clean, non-dispersed profile. Normally, a signal from 2.5 million light-years would be smeared by its passage through intergalactic plasma, but this one was sharp, suggesting a strange source or an unknown propagation mechanism. Furthermore, the signal was almost completely unpolarized, ruling out the highly polarized beams we see from pulsars, making its origin a profound puzzle.
The belt response.
Here's where the timeline gets bizarre. Exactly 16 minutes after that strange radio signal vanished, Earth's shield flinched. 16 minutes, not instant, not hours later. NOAA's GOES-18 satellite, in a geostationary orbit 35,786 kilometers high, detected a sharp, alarming uptick in high-energy electron counts from its SEISS instrument, specifically in the greater than 2 MeV energy channel. These are the killer electrons that can cause deep dielectric charging, building up static inside a satellite's components until it discharges, frying the electronics. The outer Van Allen belt had twitched violently. Flux readings jumped by 40% in under 3 minutes from a baseline of roughly 10 to the 4 to 1.4 times 10 to the 4 particles per square centimeter per second. While a major solar storm can cause increases of 1,000% or more, this event's rate of change was unprecedented for non-storm conditions. This was confirmed by Los Alamos sensors and a brief 5 to 10 nanotesla fluctuation on ground magnetometers in Tromsø, Norway. A tiny tremor compared to Earth's 65,000 nanotesla polar field, but unmistakable. Something had nudged the belts with surgical precision.
NASA's response protocol.
When our planet's radiation shields move that fast and the sun isn't the culprit, you don't panic. You execute a playbook. Step 1, call the Space Weather Coordination Center. Step 2, pull data from the DSCO-VR satellite, positioned 1.5 million kilometers away at the L1 Lagrange point. On October 1st, that data showed a placid solar wind speed of just 385 kilometers per second, a low density of 4 protons per cubic centimeter, and a stable, northward interplanetary magnetic field, or B's component, of +2 nanotesla, the very definition of calm. That's when you escalate to level 2, waking up officials like Dr. Clinton Wallace, the director of NOAA's Space Weather Prediction Center in Boulder, Colorado. This protocol involves checking astronaut radiation exposure on the ISS, which is carefully kept below a 50 millisievert annual limit, a stark contrast to the 2.4 millisieverts an average person receives on Earth in a year. Exceeding that limit can ground an astronaut for life. Even the United States Space Force's 18th Space Defense Squadron, responsible for tracking space objects and events, found no corresponding debris collision or on-orbit event that could explain the signal. The playbook had failed.
The physics mystery.
This is where the real head-scratching begins, because the data breaks our models in 3 specific ways. First, the 16-minute lag. A direct electromagnetic hit should have been instant. The delay suggests a cascade. Perhaps the radio burst triggered a slower-moving, ultra-low frequency wave in the magnetosphere, which travels at only a few hundred kilometers per second. Over the vast 100,000 kilometer scale of the outer belt, this travel time fits the 16-minute window perfectly. Second, the 408 MHz frequency. It's suspiciously close to bands that plasma physicists like Dr. Richard Thorne of UCLA know can stir up electrons through wave-particle interaction. His research focuses on natural, Whistler mode chorus waves in the few kilohertz range. It's plausible the 408 MHz signal created a beat frequency that fell directly into this highly resonant band. Third, the signature. Data hinted at sharp changes in pitch angle, concentrated around an L shell of 4.5. A key region in the outer belt. This is the precise signature of resonant pitch angle scattering, where electrons are nudged into the loss cone and dumped into the atmosphere.
Historical surprises.
Before we dismiss this, let's be clear. The Van Allen belts have shattered our understanding before. In September 2012, NASA's Van Allen probes found a third radiation belt at an L shell of approximately 3.5, a region previously thought incapable of sustaining trapped particles. It materialized, held steady for 4 weeks, and then was annihilated by a powerful solar shockwave. Lead investigator Daniel Baker stated plainly, "We were wrong." Then in 2014, the same probes confirmed the impenetrable barrier at 7,200 kilometers altitude, a discovery detailed by NASA's Dr. Sri Kanikal. Ultra-relativistic electrons simply cannot penetrate it, bounced back by a wall of plasma-spheric hiss waves. For context, we must also remember the Halloween storms of 2003, a series of intense solar events that damaged dozens of satellites and caused a power outage in Sweden, reminding us of the belt's destructive potential. These historical precedents demand that we take even the most unusual data seriously, because our models have been proven incomplete time and time again.
The resonance mechanism.
So, how could a faint distant signal possibly affect a planetary system? Well, think about pushing a child on a swing. You don't need immense strength, you need resonance. The Van Allen belts are a resonance system. The 408 MHz burst was like a perfectly timed push. The energy, though weak, may have generated a harmonic that fell into the kilohertz range of natural plasma waves, like the chorus waves studied by Dr. Richard Thorne. These waves, which sound like birds chirping when converted to audio, are incredibly efficient at accelerating electrons. A 100 keV electron can be boosted to over 1 MeV in just a couple of hours inside a strong chorus event. The Andromeda signal didn't need to be a sledgehammer, it just needed to be the right tuning fork. It likely acted as a catalyst, not the source of the energy itself. It unlocked the potential energy already stored in the magnetosphere. Triggering a release, much like a tiny spark, can ignite a huge explosion. This is a known process called a substorm, but it has never, ever been seen triggered by a non-solar, external pulse.
Real-world consequences.
This isn't just an academic puzzle, it has immediate, real-world consequences. The United States Department of Defense operates the GPS system, which relies on signals like the L1 frequency at 1,575.42 MHz. An unexpected increase in total electron content can delay that signal by tens of nanoseconds, translating to several meters of position error. For the FAA's WAAS, used for precision aircraft landings, this could be catastrophic. The 1989 Quebec blackout was caused by geomagnetically induced currents exceeding 100 amperes that saturated transformer cores, causing them to overheat and fail. That event cost an estimated $2 billion in today's money. We saw another stark reminder in February 2022, when a minor geomagnetic storm increased atmospheric drag at a low altitude of 210 kilometers, causing SpaceX to lose nearly 40 brand-new Starlink satellites. This event shows how sensitive even low Earth orbit is, and the outer belts are far more volatile. An unpredictable trigger makes risk assessment for our $1.7 trillion space economy nearly impossible.
Testing the hypothesis.
So, how do we prove this wasn't a coincidence? You follow a strict scientific playbook. Step 1 is timestamp alignment with sub-millisecond precision across multiple observatories. Step 2 is spectral analysis of future bursts to see if they again match known resonance bands. Step 3 is global confirmation from instruments like the Themis satellites, which provide multi-point measurements within the magnetosphere. The most critical test, Step 4, is repetition. To reach the 5 sigma level of certainty required to announce a discovery, a 1 in 3.5 million chance of being a random fluke, this exact chain of events must be observed again. As astrophysicist Avi Loeb often stresses, null results are just as important. Telescopes like Canada's CHIME, an FRB finding machine, will now be cross-referencing their detections with real-time space weather data. If another Andromeda burst is detected with no corresponding belt response, that data is crucial for constraining the theory. Science advances by disproving ideas just as much as by proving them.
Background science explained.
Let's quickly break down the fundamentals. The Van Allen belts, discovered in 1958 by James Van Allen using data from Explorer 1, America's first satellite, are 2 zones of radiation. The inner belt, from 1,000 to 6,000 kilometers, contains high-energy protons of 10 to 100 MeV. The outer belt, from 15,000 to 25,000 kilometers, is mostly electrons of 0.1 to 10 MeV. For comparison, a medical X-ray particle is in the kilo-electron-volt range, thousands of times weaker. The groundwork for this was laid by Norwegian scientist Christian Birkeland, who used his Torella experiments to show how particle beams created auroral rings, a century before we confirmed it with satellites. A key feature is the South Atlantic anomaly, a region where the inner belt dips to just 200 kilometers altitude due to the offset between Earth's geographic and magnetic poles. Satellites like the Hubble Space Telescope must power down sensitive instruments when passing through it to avoid damage from this concentrated radiation. We are left with a profound and unsettling mystery. The facts are on the table. A radio burst from the Andromeda sector was observed, and 16 minutes later, Earth's radiation belts responded in a way our models could not explain. The correlation is documented, the physics is plausible, but the interpretation remains open. Was this a 1 in a billion cosmic coincidence, or have we discovered a new coupling mechanism between our planet and the distant universe? The only way to find out is to keep watching, to test the hypothesis with rigorous, repeatable science. This is how true discovery works, not with hype, but with data. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching InnoVision Tech.